A stone arch stands today that carried Roman legions 2,000 years ago. It was built without steel or concrete, yet it outlasts countless modern structures. This video uncovers the hidden genius that allowed ancient bridges to survive for millennia. You will learn the precise engineering secrets that gave these structures their incredible longevity. How did builders with only simple tools create monuments that defy time itself? What forgotten wisdom is locked within their stones? We will journey from Roman aqueducts to Incan mountain crossings to find the answers. These ancient marvels hold urgent lessons for our own future of building and design. What do you believe is the most important ingredient for creating something that truly lasts? Deep in a sun-baked quarry, a master mason runs a calloused hand over a block of granite. He is not just choosing a stone, he is selecting a partner for a project that must stand for centuries. The very identity of an ancient bridge was forged in places like this, with materials pulled directly from the local landscape. Builders relied almost exclusively on what the earth provided nearby. Stone, wood, brick, and lime mortar were not just convenient choices. They were strategic ones, each possessing inherent properties that the builders learned to harness with incredible skill. The Roman architect Vitruvius left detailed notes on this very process. He instructed builders to seek out stone that was flawless, free of cracks, and possessed a natural resistance to the elements. Granite and limestone were especially prized for their immense compressive strength, their ability to bear massive weight without crumbling. Think of it like a sturdy wall supporting a heavy roof. The stone simply would not be crushed. For moving parts or temporary supports, dense hardwoods like oak offered a different kind of strength, one of flexibility and toughness. But perhaps the most revolutionary material was born from fire. The Romans discovered that a volcanic ash called pozzolana, when mixed with lime and water, created a magical substance. This hydraulic mortar would not just set underwater, it would actually grow harder and more resilient over time, forming an unshakable grip for the piers of bridges that had to stand in rushing rivers. So the next time you see an ancient stone bridge, do not just see a structure, see a dialogue between the builder and the land itself. The local geology did not just supply the materials. It whispered the blueprint, guiding hands to create a bridge that was, in essence, an extension of the earth. This profound connection to place was only the beginning. The real magic happened when these perfectly chosen materials were assembled using techniques that defied their apparent simplicity. That final, perfectly shaped stone, the keystone, slides into place. In that moment, a collection of individual blocks transforms into a single, unified structure. This is the magic of the arch. It is engineering's most perfect form, a shape that turns the relentless downward pull of gravity into its own source of strength. Every stone in the arch, known as a voussoir, is precisely cut. Once assembled, each one presses firmly against its neighbors. This force, called compression, travels smoothly along the arch's elegant curve, pushing outward and downward into the massive supports at either end, the abutments. The entire structure enters a state of perfect equilibrium, locked in a silent, permanent embrace. Roman engineers like Marcus Vipsanius Agrippa mastered this principle on a colossal scale. They built not just for their own time, but for the ages. Look at the Pont du Gard in southern France. Its 3 tiers of soaring semicircular arches do not simply hold up a water channel. They demonstrate a profound understanding of nature's laws. The arch's stability meant it could bear the immense, constant weight of the aqueduct itself. the dynamic force of marching legions, and the sudden, violent pressure of river floods. Why does this simple curve possess such timeless strength? The answer lies in the way it channels force. Instead of fighting gravity, the arch welcomes it, using that energy to bind itself ever tighter. This was not just craftsmanship. It was a deep, intuitive application of mathematical principles that dictated every proportion, every curve, ensuring the bridge would not just stand but endure. Geometry was the silent language spoken by ancient engineers, a system of perfect lines and ratios that translated into unshakable stability. Visualize an architect at a wooden table, his tools not complex machines but a simple compass and a straight edge. With these, he would lay out the entire design for a bridge, every dimension dictated by geometric principles and harmonic ratios. The Roman writer Vitruvius championed this approach, arguing that structures reflecting the symmetry and order found in nature and the cosmos were inherently more beautiful and, crucially, more durable. For a bridge, this was not an abstract artistic choice. It was a precise engineering calculation. The rise of an arch relative to its span, the thickness of a pier compared to its height, all followed established proportional rules. These rules, often based on ratios like the golden section, were not arbitrary. They were the key to optimizing strength. A perfect example stands in Spain, the Alcantara Bridge. Its 6 majestic arches are not just impressive to look at. They are a masterclass in applied mathematics, their proportions calculated to ensure that the immense weight of the structure and the forces acting upon it were distributed evenly throughout the entire form. This prevented stress from concentrating at any single weak point, the kind of localized failure that could bring down a lesser design. So how did a mathematical ideal translate into physical endurance? The answer lies in the seamless marriage of this perfect geometry with the hands of the master craftsmen who brought it to life. The stone itself held the secret, but it was the mason's hand that unlocked it. A master craftsman would spend days, sometimes weeks, on a single block. With nothing more than a hammer, a chisel, and an experienced eye, he would chip and smooth the stone until its surface was a complex landscape of subtle angles and curves. This was not about creating a perfectly flat face. It was about sculpting a unique 3-dimensional puzzle piece that would mate flawlessly with the stones around it. The goal was a perfect transfer of force, stone to stone, with no gap for movement or weakness to form. This art, known as Ashlar Masonry, was practiced to an almost unbelievable degree by the Inca. Their walls, built without any mortar, fit together so tightly that you cannot slide the edge of a piece of paper between the stones. This was not for aesthetic beauty alone, though the result is breathtaking. This precision created a structure that moved as a single, solid mass during earthquakes, the stones shifting and settling without collapsing. The Romans, in their pursuit of scale, developed ingenious machinery to place these perfectly cut stones. They employed massive treadwheel cranes, powered by men walking inside a giant wheel, to lift blocks weighing many tons into their exact positions high on an arch. What does this obsessive attention to detail reveal? It shows that the builders understood a fundamental truth. The best geometry in the world is useless without perfect execution. The strength of the arch depended entirely on the intimate, unbroken contact between each and every stone. This was not mere construction. It was a form of physical poetry, where human skill elevated raw material into a form that could defy centuries. And this careful assembly was only possible because of a design philosophy that thought far beyond a single lifetime. Gravity itself became the architect's greatest ally. Visualize the invisible lines of force flowing through the stones of an arch, all pushing inward and downward in a state of perfect, stable balance. Ancient bridges were masterpieces of compression, a principle where materials are at their strongest when being pushed together, not pulled apart. Think of a tall stack of books. You can press down on it with tremendous force and the books will not break, but try to pull them apart and the stack immediately fails. Stone and brick are exactly the same. They possess incredible strength under compression but are weak when faced with tension, the force that tries to pull them apart. The genius of the ancient engineer was to design a structure that ensured every stone was almost always in a state of compression. The dead load of the bridge itself and the live loads from marching soldiers or rumbling carts created compressive stresses that the masonry could handle with ease. This is why the massive abutments and piers were so critical. They were not just foundations. They were anchors designed to absorb and redirect the outward thrust generated by the arch, locking that powerful compressive force into the very earth below. The sheer weight of these stone giants also made them incredibly resistant to being overturned by floods or earthquakes. Their own mass pinned them in place. How does a structure designed solely for compression endure for millennia? The answer lies in its beautiful simplicity. There are no moving parts to wear out, no metal to rust and weaken. The forces are constant and predictable, a silent, stable equilibrium proven not in a laboratory, but through centuries of relentless real-world testing. This profound understanding of physical forces was then amplified by another brilliant strategy, one that gave these stone giants the flexibility to move without breaking. A bridge did not always stand on its first attempt. Somewhere along a forgotten riverbank, the first version likely succumbed to a powerful current, its stones scattered by a force its creators had underestimated. This was not the end of the story, but a crucial chapter in it. Ancient engineering was an iterative art, a slow, patient accumulation of wisdom where every collapse and every crack taught an invaluable lesson. While triumphant inscriptions celebrate the successes, the true learning often happened in the silence of failure. Archaeologists see this evolution etched in stone itself. By comparing bridges from different eras, they observe a clear progression. Piers become thicker and more robust. Arch shapes are subtly modified, their curves optimized to better channel weight and water flow. The Romans, with their empire-wide building campaigns, were masters of this empirical process. They built frequently and in diverse locations, creating a vast, shared repository of practical knowledge. If a bridge in Gaul suffered because its piers were scoured away by a fast-moving river, the solution developed there, perhaps deeper foundations or protective starling structures built upstream of the piers to break the current, would inform the next project in Hispania. They learned by doing, by observing, and by adapting. This relentless refinement was deeply tied to the local environment. A design that worked perfectly in a calm, slow-moving river would be a death sentence for a bridge spanning a mountain torrent. The builders had to listen to the land, to understand its unique personality and its potential for violence. Their greatest teacher was not a scroll or a theorem, but the river itself. What can we learn from the mistakes buried beneath these enduring successes? That true resilience is not born from perfection, but from the humility to learn, adapt, and build again, smarter and stronger than before. This deep environmental intelligence guided them to build not just on the land, but with it, in a way that harnessed the landscape's own strength for protection. A Roman surveyor stands on a riverbank not for a day, but through the changing seasons. He is reading the water's story, learning its moods and its power, long before a single stone is cut. This deep observation was the true foundation of every enduring bridge. The genius of ancient builders was not just in how they built, but overwhelmingly in where they built. They sought a perfect partnership with the landscape, choosing locations that harnessed the environment's own strength. The single most important factor was finding stable, unyielding bedrock upon which to anchor their massive piers, moving earth and diverting rivers if necessary to reach that solid foundation. They instinctively avoided zones of violent erosion or predictable flooding, understanding that the river's path was a force to be respected, not conquered. Sometimes they went a step further, integrating natural rock outcrops directly into the bridge's design, turning the living earth itself into an abutment. A perfect example of this philosophy is the ancient Chinese Jiuzhou Bridge. Its builders did not just place it at a convenient crossing, they selected a specific point where the riverbed was naturally solid. More brilliantly, its open spandrel design, with small arches piercing the sides of the main arch, was not merely decorative. It was a stroke of hydraulic genius, allowing floodwaters to surge through the bridge itself, dramatically reducing the pressure that would otherwise batter and potentially topple the structure. This was environmental harmony in its purest form. How does choosing the right location become the first and most critical step in ensuring a bridge's millennial lifespan? It is the difference between building a dam against a relentless current and building a channel that guides that current safely on its way. This profound wisdom in site selection set the stage for the most physically demanding phase of the project, the creation of a foundation that would not falter for 1,000 years. The river itself had to be conquered before the first stone could be laid. Laborers, working in coordinated teams, would drive a double wall of thick timber planks deep into the soft riverbed, creating a temporary enclosure called a cofferdam. The water trapped inside was then relentlessly pumped out by hand-operated Archimedes screws or a chain of buckets, slowly revealing the muddy bottom. This was a race against time and the elements, an audacious act of creating a dry construction site in the middle of a flowing river. Within this precarious man-made island, the real work began. They would dig shovel by shovel through silt and sediment, not stopping until their tools struck the unyielding surface of solid bedrock. For the Romans, this was non-negotiable. On the soft, unstable banks of the Tiber, they demonstrated another technique, driving long, sharpened wooden piles deep into the ground until they reached a compact layer, creating a stable artificial platform for their massive stone piers. Look at the Pons Fabricius, still standing after more than 2,000 years. Its enduring strength comes from foundations carved directly into the tough rock of the riverbed itself. Why is this submerged struggle so critical? Because a bridge's greatest enemies are often invisible. The relentless flow of water can scour away sediment from around a shallow foundation, creating hidden cavities that undermine the entire structure. A deep, well-founded pier resists this scouring action and prevents the slow, fatal sinking known as settlement. The massive weight of the stone superstructure above was not a burden. It was a strategic asset, but only if that weight could be transferred securely into the earth. The foundation's role was to ensure that this transfer was absolute and permanent. So the true masterpiece of an ancient bridge was not the elegant arch you walk across, but the hidden, monumental effort to anchor it to the planet. This profound understanding of mass and stability was then expressed in the bridge's most visible feature, its overwhelming and deliberate heaviness. Mass itself became a form of armor. In an era before computer models and stress calculations, ancient engineers understood a fundamental truth. If you cannot avoid a force, you must outweigh it. The colossal bulk of an ancient bridge was not a clumsy overuse of material. It was a deliberate, calculated strategy. That immense stonework generated powerful inertia, a natural resistance to being moved. Think of trying to push a small pebble versus a massive boulder. The pebble skips away with the slightest touch, while the boulder remains steadfast. Ancient bridges were designed to be the boulder. Their sheer mass pinned them to the earth, making them incredibly resistant to the shoving power of floodwaters or the shaking of an earthquake. This principle is written in stone across the Roman world. Look at the surviving piers of their bridges, often many times thicker than what a modern engineer would calculate as strictly necessary. This was a generous safety factor built not on paper but in granite. The weight ensured the structure's center of gravity remained low and stable, causing the entire bridge to behave as a single, monolithic entity that would rather settle slightly than fracture. Trajan's bridge across the Danube was the ultimate expression of this philosophy. Though only ruins remain, historical accounts describe a staggering feat of mass and scale, with wooden arches supported by 20 massive stone piers. How does simply being incredibly heavy contribute to longevity? It creates a structure that endures through sheer, unyielding presence, a monument that chooses stubborn stability over delicate efficiency. And yet, this apparent rigidity was masterfully balanced with a hidden capacity for movement. A rigid stone bridge is not as motionless as it appears. Each summer day, its stones expand almost imperceptibly under the sun's heat. Every winter night, they contract in the cold. Over centuries, this slow, rhythmic breathing could shatter a structure that fought the movement. Ancient builders possessed an intuitive genius for this reality. They understood that to survive the ages, their creations needed not just strength, but a kind of forgiveness. They designed for movement, embedding flexibility directly into the stonework. One of their most powerful tools was the mortar itself. The lime-based mortars they used were deliberately mixed to be less rigid than the stone. When slight shifts occurred from thermal expansion or ground settlement, this softer mortar would absorb the stress, cracking minutely and then recrystallizing over time, a self-healing property that prevented catastrophic failure in the main stone blocks. Look closely at some ancient Roman bridges, and you might see another brilliant adaptation: segmented arches. Instead of a single, unbroken arch ring, the Romans often built their arches as multiple, independent rings of stone placed side by side. This meant that if one ring settled slightly due to a soft spot in the foundation, it could do so without pulling the entire arch down with it. The neighboring rings would remain, carrying the load and preserving the structure's integrity. This capacity to tolerate and dissipate movement was a hallmark of truly resilient design. How does a structure become stronger by learning to yield? It is the same principle as a tall tree bending in a storm instead of resisting until it snaps. This deep understanding of dynamic forces, of designing for the real world of constant, tiny changes, separated the millennial survivors from those that collapsed within a few generations. And this foresight extended to defending the bridge from a far more aggressive and visible enemy, the relentless carving power of flowing water. A bridge did not merely stand against the river. It learned to dance with it. The most brilliant ancient designs incorporated features that turned destructive forces into passing events. Look at the sturdy, rounded piers of a medieval bridge, their upstream ends often tapered to a sharp point. These were not just supports, they were called cutwaters, and they functioned like the prow of a ship, expertly slicing through onrushing floodwaters. This elegant shape did two things with life-saving efficiency. It dramatically reduced the pressure of the water slamming against the pier itself, and it guided logs and other debris smoothly around the structure instead of allowing them to pile up and form a dam of destruction. This single, thoughtful adaptation turned a solid obstacle into a dynamic partner with the river. In regions shaken by earthquakes, the approach was different but equally ingenious. In ancient Persia and China, builders understood that a rigid structure would be shaken apart. Their solution was to introduce controlled flexibility. They might use stone blocks that were intentionally not locked together with rigid mortar, or incorporate flexible timber beams within a stone framework. During a tremor, these elements would allow the structure to sway, shift, and absorb the seismic energy, the stones grating and settling without losing their fundamental integrity. The Ishak Pasha Bridge in Turkey stands as a powerful testament to this philosophy, its design allowing it to endure centuries of tectonic shifts. How did they build structures that could dance with the earth? They recognized that nature's power could not be blocked, only channeled and absorbed. This inherent toughness was a form of strategic forgiveness. A bridge might suffer localized damage, a cracked stone, a shifted block, but its core design prevented a total, catastrophic collapse. This meant it could be repaired, its life extended generation after generation. And that capacity for repair points to the final, crucial layer of their longevity, a living tradition of care that wove the bridge directly into the fabric of human society. A bridge's endurance was never just a matter of stone and mortar. It was a promise written into the life of the community itself. These structures were not passive monuments but vital organs in the body of a civilization, pulsing with the lifeblood of commerce, soldiers, and ideas. A collapsed bridge meant more than an inconvenience. It meant severed supply lines, isolated towns, and strategic vulnerability. This profound importance forged a powerful social contract, a collective understanding that the bridge must be maintained at any cost. The Roman state recognized this reality with military precision. Their legendary roads and the bridges that carried them were the empire's nervous system, allowing legions to march at incredible speed and the riches of the provinces to flow back to Rome. The maintenance of these vital crossings was not left to chance. It was a formal, state-funded priority, with engineers and laborers assigned to ensure that wear and tear from countless carts and marching feet did not lead to structural decay. This was an investment in power, and it paid for itself 1,000 times over. In medieval Europe, the model changed, but the principle remained. A local lord or a wealthy religious order would often finance a bridge's construction, not purely from charity, but because a functioning bridge generated a continuous stream of toll revenue from merchants and travelers. This created a self-perpetuating cycle. The income from the bridge directly funded the repairs it needed to keep generating that income. The bridge became a financial asset, and protecting that asset was simple economics. Why does a bridge's value to its society so directly dictate its physical lifespan? Because a treasured and useful structure is watched over. A cracked pier or a dislodged stone would be reported quickly and repaired promptly by those whose livelihoods depended on the crossing. A minor issue left unattended for a few years can become a gaping wound that dooms the entire structure. But with a community invested in its survival, small problems were fixed while they were still small. This ongoing care was the final, indispensable layer of preservation, a living tradition of stewardship that wrapped the stone and geometry in a protective layer of human attention. This responsibility was often formalized in remarkable ways, through endowments and even sacred duties that bound the community to the bridge for generations. This responsibility was woven into the very fabric of daily life. In a medieval village, the sound of the church bell might not signal a service, but a call to communal labor. Every able-bodied person would gather, not to build something new, but to care for what they already had, spending a day each year clearing branches, silt, and debris from the foundations of their local bridge. This was not an occasional chore. It was a ritual of survival, a continuous, often formalized tradition of maintenance that was as vital to a bridge's longevity as the stone from which it was made. Across cultures, specific laws and customs emerged to codify this duty. In some places, a wealthy merchant's guild took on the responsibility as a pious act, ensuring the trade routes that enriched them remained open. In others, a nearby monastic order saw the upkeep of a bridge as a sacred charge, a physical manifestation of their duty to aid travelers. The community itself was often bound by law to contribute labor or funds, recognizing that the bridge's collapse would mean their own economic and social isolation. What did this relentless care actually involve? It was humble, patient work. It meant clearing invasive vegetation whose roots could slowly prise stones apart. It involved repointing mortar joints, carefully scraping out the old, crumbled lime and pressing in new, preventing water from seeping into the core of the structure. Most importantly, it meant keeping the water channels around the piers clear, ensuring that the river's flow could not scour away the hidden foundations. The story of London Bridge is the ultimate testament to this philosophy. It was not one bridge that stood for 600 years, but a constantly evolving entity. It was maintained, repaired, and rebuilt section by section over centuries, a living structure perpetually renewed by the hands of each new generation. How does the simple act of regular cleaning add centuries to a structure's life? It stops the cascade of failure. A single blocked water channel leads to accelerated scouring, which undermines a pier, which transfers uneven weight to an arch, which then cracks and collapses. By addressing problems when they were tiny and required only a day's labor with simple tools, this culture of maintenance prevented the kind of catastrophic, irreparable damage that would require a king's ransom to fix. The original builder's genius lay in the stone and the arch, but the bridge's millennial life was a gift from every generation that chose to clear the debris and repoint the mortar, actively preserving a legacy they had inherited. This long-term perspective was a form of wisdom, a stark contrast to the short-term thinking that often governs our world today. A Roman cart laden with olive oil amphorae would have crossed a bridge at a walking pace, its wooden wheels distributing a slow, rhythmic pressure. This gentle, predictable load stands in stark contrast to the destructive forces that assault a modern overpass. Today, a single heavy truck does not just add weight. It sends high-frequency shockwaves pulsing through the structure, a relentless drumbeat of vibrations that slowly, invisibly fatigues the steel and concrete. Ancient bridges were spared this brutal, cyclical punishment. Their world was one of static loads, the steady downward pressure of pedestrians, the deliberate roll of an ox cart, the synchronized tread of a marching legion. These forces were massive, but they were fundamentally different. They were slow and sustained, not rapid and jarring. The stress cycles they created remained far below the material's fatigue limit, that critical threshold where repeated bending and flexing begins to create microscopic cracks that grow over time. Beyond the absence of vibrational torture, these stone giants were also untouched by the chemical warfare waged on modern infrastructure. Think of the corrosive de-icing salts sprayed onto winter roads today, seeping into every pore of reinforced concrete, attacking the steel rebar inside until it rusts, expands, and bursts the structure apart from within. Ancient masonry knew no such internal enemy. The stone and lime mortar were not vulnerable to these chemical agents, and the absence of internal metal reinforcement meant there was nothing to corrode. Even the air itself was gentler, free from the acidic pollutants that now eat away at stone facades in our cities. So, in what way did their historical context become a form of protection? Their survival is not just a testament to how they were built, but also to the comparatively peaceful world they inhabited. They never had to face the 24/7 assault of industrial society. This historical accident of a gentler usage profile granted them a quiet, uninterrupted lifespan, allowing their inherent strength to face only the tests of time and nature, not the relentless grind of modern industry. A tiny fracture in the mortar was not a final verdict, but an invitation for the material to heal itself. This was the quiet genius of lime-based mortars. When rainwater seeped into a hairline crack, it dissolved particles of free lime that were still present within the matrix. As this lime-saturated water met the carbon dioxide in the air, a slow-motion miracle occurred. The solution crystallized, forming a new layer of hard, stony calcite that gradually filled the gap from the inside out. This process, known as autogenous healing, meant that a bridge could literally stitch its own wounds over time, given the seasons and the rain. It was a living material in the most patient sense. The Romans elevated this principle with their pozzolanic mortar. By mixing lime with volcanic ash, they created a substance that did not just heal, but actually grew stronger when exposed to water, its chemical bonds tightening over centuries. Compare this to modern Portland cement, which, while immensely strong initially, is often more brittle. A crack in modern concrete tends to be a permanent flaw, a point of weakness where water intrudes, freezes, and widens the breach year after year, often accelerating corrosion in any internal steel reinforcement. So why did we abandon such a resilient technology? The answer lies in the relentless pace of the modern world. Portland cement sets quickly, allowing for rapid construction, while traditional lime mortar cures slowly, demanding time and patience that contemporary projects rarely afford. We traded long-term resilience for immediate speed. This self-healing capacity reveals a profound design philosophy. The ancients did not seek to create a perfectly static, unyielding object. They built with an understanding that their materials and the world were in a constant state of flux. They engineered for adaptation, not just for initial perfection. The stone provided the enduring skeleton, and the living mortar acted as a resilient, regenerative tissue, together forming a partnership that could endure the slow, patient work of time. Granite does not surrender to the rain. A block left exposed for 2 millennia will show only a weathered skin, its inner heart as solid as the day it was quarried. This is the profound permanence of stone, the primary reason these ancient bridges could stare down the centuries. Environmental weathering from freezing rain, scouring winds, and baking sun acts with a geological slowness on dense, high-quality rock. The real genius of the builders was in knowing which stones held this defiance within them. They were master geologists of their local landscape, understanding that not all stone was created equal. In a wet, freezing climate, porous sandstone could be a death sentence. Water would seep into its tiny pores, freeze, and expand, slowly prying the stone apart from the inside in a process called spalling. But in the same environment, granite, with its immense hardness and low porosity, would laugh at the frost. Its tight crystalline structure gave water almost no purchase, allowing only the slowest, most superficial wear. This careful selection was a form of long-term prophecy. The builders knew that even if a bridge was abandoned, if its mortar was eventually washed away by neglect, the core skeleton of stone would remain standing, its essential integrity preserved. Why is this humble, ancient material one of the most permanent humanity has ever used? Because stone does not rust, it does not rot, and it does not burn. It endures through a simple, unyielding physical presence. The brilliant structural forms of the arch and the vault were perfectly matched to this enduring character, creating a synergy where material and design amplified each other's strengths for a 1,000-year lifespan. A rope bridge sways high above a mountain gorge, its fibers groaning under the strain. It is the antithesis of a solid Roman arch, yet it obeys the very same principle. The builders did not fight the nature of their materials. They listened to them, and then they built a form that let those materials sing. This is the profound synergy of form and material, the secret harmony that separates a structure that merely stands from one that truly endures. The elegant arch is not just a shape, it is the ultimate expression of stone's character, a form that forces every block into a state of pure compression, the one type of stress stone handles with glorious, unyielding strength. Conversely, the ancient Incan rope bridges demonstrate a parallel genius. The builders knew that plant fibers like iku grass possessed incredible tensile strength, the ability to resist being pulled apart. They would never carve a beam from stone and expect it to span a chasm like a rope. Instead, they braided these fibers into massive cables, using a form that placed the entire structure in tension, a continuous, balanced pull that the material was born to handle. The form celebrated the material's inherent gift. How does respecting this innate character lead to more enduring designs? It eliminates internal contradiction. A design that forces a material to perform against its nature creates built-in weakness, a flaw that time will inevitably find and exploit. The Roman stone arch and the Incan rope bridge, though worlds apart, both represent a holistic philosophy. The builder's first question was not, "What do I want to build?" It was, "What can this material do?" The answer to that question then whispered the shape of the bridge itself. This deep, intuitive partnership between the craftsman's hand and the earth's offering guided every cut, every knot, and every placement, creating a resilience that feels less like engineering and more like a natural law. A master builder might lay the first stone knowing he would never cross the finished span. These projects unfolded on a timescale that is almost incomprehensible today, measured not in fiscal quarters but in human lifetimes. A single bridge could take 50 years to complete, its construction site a permanent fixture in the town, a place where a young apprentice would learn his craft and one day become the master, teaching his own son. This generational continuity was not a sign of inefficiency. It was a strategic advantage, a deliberate and unhurried pace that allowed the materials and the structure itself to find their natural equilibrium. There were no shareholders demanding a return on investment by next year, no political pressure to cut a ribbon before an election. This freedom from modern financial pressures meant builders could let their lime mortars cure for a full year, or even longer, achieving a final strength and resilience that quick-setting modern cements cannot match. Stones quarried for the arches were not rushed into place. They were left to season in the open air, allowing internal stresses to relax and hidden flaws to reveal themselves before they were entrusted with a load that had to last 1,000 years. This slow, incremental construction also acted as a continuous, real-world stress test. As each new arch was completed and the scaffolding removed, the structure would naturally settle under its own immense weight. The builders would watch, patiently observing for any signs of movement or hairline cracks. They had the time to make subtle adjustments, to add extra support, or to simply wait until the bridge had fully acclimated to the new load before proceeding to the next section. This was construction as a form of conversation with the building itself, a dialogue of constant, minor corrections. What is the true cost of our modern obsession with speed? We have gained immediate convenience, but we may have sacrificed the millennial patience that allowed stone and mortar to fuse into a single, unbreakable entity. The greatest luxury afforded to these ancient builders was not gold or advanced machinery, but the one resource we are most reluctant to spend today, time itself. The Pont du Gard does not simply cross a river. It strides across the valley on 3 soaring tiers of arches, a symphony in golden limestone that has carried water for legions and now carries our wonder. This aqueduct bridge in southern France is a perfect case study, a structure that has endured for nearly 2,000 years by masterfully applying every principle of ancient resilience. Its builders used stone quarried from the very hills it traverses, a local limestone that became the flesh and bone of the monument. To lift these massive blocks, some weighing over 6 tons, into the air, they employed a sophisticated array of human-powered cranes and complex pulley systems, a coordinated ballet of muscle and ingenuity that placed each stone with breathtaking precision. Look closely at the grand arches of the lower tiers. You will see no mortar holding the stones together. The masonry is so exact, the joints so perfectly fitted, that the structure stands through friction and compression alone, a three-dimensional stone puzzle locked in permanent equilibrium. Yet for all its immense presence, the Pont du Gard possesses a surprising lightness. The upper tier, which supported the water channel itself, is punctuated by a series of smaller arches. This was not merely an aesthetic choice, it was a stroke of material efficiency, reducing the dead weight of the bridge without sacrificing an ounce of strength, a refined understanding of how to use just enough stone and not a block more. How did this specific design help it survive centuries of river floods and long periods of neglect? Its gentle, consistent gradient was key. The water flowing from the distant spring descended only 17 meters over its entire 50-kilometer journey, a drop of just 1 in 3,000. This ensured a steady, non-violent flow that did not erode the channel or shake the foundations, even during torrential rains. The arches themselves were engineered to handle immense hydraulic pressure, their robust piers acting as steadfast anchors against the river's fury. Its story of adaptation is as remarkable as its construction. After the fall of Rome, it served as a fortified toll bridge in the Middle Ages, its enduring strength finding new purpose. Each new era found a use for it, which in turn justified its maintenance and preservation. The Pont du Gard is not one lesson, but many. It is the story of perfect geometry married to local material, of immense strength achieved with elegant economy, and of a structure so inherently useful that humanity could not bear to let it fall. While Roman arches soared with semicircular confidence, a different kind of genius was taking shape on the other side of the world. In 7th century China, the master builder Lai Chun confronted a wide, unpredictable river with a radical idea. He would not build a towering, heavy bridge that fought the water's power. Instead, he would build a bridge that invited the river to share its burden. The result was the Anji Bridge, a structure that shattered 1,000 years of architectural convention. Its most stunning feature is its form. It is not a semicircle but a shallow, graceful arc, a segment of a much larger circle. This seemingly simple change was a stroke of engineering brilliance. A shallow arch exerts far less outward thrust on its banks, meaning the massive, heavily fortified abutments of Roman bridges were no longer necessary. Lai Chun could anchor his bridge with lighter, simpler supports, dramatically reducing the amount of stone required and the cost of construction. The bridge became a lesson in elegant economy, proving that immense strength did not always demand immense mass. But his innovation did not stop there. He pierced the solid spandrels, the triangular areas between the arch and the deck, with 2 smaller arches on each side. These open spandrels were not decorative. They were hydraulic escape valves. When the river swelled with monsoon rains, the floodwaters would not batter against a solid wall of stone. They would surge straight through these openings, passing through the bridge itself and reducing the destructive pressure on the structure by nearly a fifth. How did this design challenge conventional arch theory? It redefined the arch's very purpose from a static load-bearer to a dynamic, interactive system. The bridge was no longer an obstacle but a collaborator with the forces of nature. Its resilience is woven into its very fabric. The main arch is not one single rib of stone, but 28 individual arches laid side by side, each one a self-contained structural system. This segmented design granted the bridge a subtle flexibility. If one section settled due to a soft spot in the foundation, or if an earthquake shook the land, the neighboring arches could remain intact and carry the load, preventing a catastrophic chain reaction. The Anji Bridge, built from local limestone, has withstood 10 major floods, countless earthquakes, and the relentless wear of 14 centuries. It stands as a testament to a different cultural philosophy, one that sought harmony with natural forces rather than dominance over them. It asks us a profound question: is the ultimate form of strength found in rigid resistance, or in the intelligent ability to yield and adapt? High in the thin air of the Andes, a different kind of bridge defies the dizzying chasms. Its floor sways with every step, a living, breathing pathway woven not from stone, but from the very grass that blankets the mountainsides. The Inca confronted a landscape of impossible gorges, where building with heavy, quarried stone was not just impractical, but often impossible. Their genius was to look at the humble iku grass and see not a weak plant, but the potential for immense tensile strength. They mastered a material completely opposite to Roman granite, yet their solution was no less brilliant. They would gather this grass and painstakingly braid it into thick ropes. These ropes were then twisted into larger cables, and those cables were braided again into the final, massive cords that would form the bridge's very being. The process was a masterpiece of applied physics, creating a structure that existed entirely in tension, a perfect match for the natural strength of the fibers. At each end of the gorge, they built solid stone abutments, anchoring the woven wonder to the living rock of the mountain itself. The result was a suspension bridge that could span distances stone arches could never dream of, carrying people and llamas across voids that would OTHERWISE Chinese letter entire communities. But the most profound secret of this bridge was not in its construction, but in its scheduled demise. The Cutwaters Bridge, like all in its kind, was not built to last forever. It was designed to be rebuilt year after year in a communal ritual that transformed maintenance into a form of worship. The local communities saw this not as a burden, but as a sacred duty, a pact between the people and the mountain. For 3 days, families would gather, working together to tear down the old bridge and weave a new one in its place, using techniques passed from father to son, from mother to daughter for generations. The knowledge of the knots, the tension, the precise braiding of the cables was not written down in any manual. It was carried in the muscles and the memories of the people. In this act, the bridge achieved a different kind of immortality. Its physical form was always fresh, never given the chance to grow weak with age. Its design was perpetually validated, its construction secrets kept alive through constant practice. So how does a bridge that is deliberately temporary achieve a form of immortality? The answer is that its longevity does not reside in the material object, but in the enduring human system that sustains it. The bridge itself is merely the current manifestation of a timeless knowledge, a cycle of death and rebirth that has outlasted empires. This shifts our entire understanding of survival from the permanence of the object to the resilience of the tradition. It asks us whether a stone arch that stands for 2,000 years is truly more permanent than a grass bridge that has been faithfully renewed for 500. One endures through the stubbornness of its material, the other through the unwavering commitment of its people. The formulas for Roman concrete and pozzolanic mortar vanished from the world for over 1,000 years. With the fragmentation of the Roman Empire, the vast, centralized system of engineering knowledge shattered. The master masons and architects who understood the precise mix of lime, volcanic ash, and aggregate were gone, and their trade secrets faded into the ruins they left behind. The medieval and Renaissance builders who followed could only look upon structures like the Pantheon with awe, unable to replicate the material that formed its magnificent, unsupported dome. They were inheritors of a treasure they could no longer access, a technological peak that had been lost to time. It was not until the 1700s and 1800s that a new age of engineers began to catch up, not through recovered scrolls, but through the slow, painstaking work of scientific inquiry. Figures like Giovanni Polni studied the stability of the dome of St. Peter's, using nascent mathematical principles to formalize what the Romans had understood through sheer, brilliant empiricism and generations of trial and error. They were beginning to translate an ancient, intuitive language into the cold, hard logic of equations. Today, this process of rediscovery has accelerated into a high-tech detective story. Scientists now use electron microscopes to examine the molecular structure of 2,000-year-old Roman concrete, finding within it crystalline formations that act as a self-healing agent, locking cracks before they can spread. Engineers employ finite element analysis, a computational method that creates a digital twin of an ancient bridge, allowing them to apply virtual floods and earthquakes to watch how the invisible lines of force dance through the stones, almost always confirming the structural perfection of the original design. This modern validation is not just a tribute to the past, it is actively shaping a more resilient future. The rediscovery of Roman concrete, for instance, has inspired new formulas for modern, eco-friendly cements that require less energy to produce and possess similar self-healing capabilities. We are now looking to the ancient world not as a museum of dead techniques, but as a living library of sustainable solutions. So what can we, with all our satellites and supercomputers, still learn from these masters? We are learning the profound value of patience, of designing with time itself as a material. We are learning to listen to the inherent intelligence of local materials and to build systems that cooperate with natural forces rather than attempting to dominate them. The conversation with the ancients has been reopened, and their answers are guiding us toward building a world meant to last. The oldest engineering ideas are now shaping the most cutting-edge designs. In an era defined by climate change and resource scarcity, contemporary engineers are not just admiring ancient bridges, they are actively reverse engineering their secrets to build a more resilient future. The principle of designing for compression is making a dramatic comeback. Instead of relying on energy-intensive steel reinforcement to handle tension, innovators are creating new forms of compression-only architecture. Think of vaulted ceilings and arched forms built from precisely cut blocks or even 3D printed components, where the shape itself carries the load, eliminating the need for carbon-heavy rebar. This is not mere nostalgia. It is a recognition that the most elegant solutions are often the simplest and most fundamental. The ancient mandate to use local materials is also being reborn as a cornerstone of sustainable design. Why transport tons of steel and concrete across continents when you can use stone, earth, or timber sourced from the surrounding landscape? This drastically reduces the embodied energy, the total carbon cost of getting materials to a site, and creates structures that are inherently suited to their local climate and geology. But perhaps the most significant revival is happening at the molecular level with a renewed interest in lime-based concretes. Modern Portland cement is a major contributor to global carbon emissions. In contrast, lime production requires lower firing temperatures, resulting in a significantly smaller carbon footprint. And just like its Roman predecessor, lime mortar possesses that magical, patient ability to self-heal microcracks, a property modern scientists are feverishly working to replicate in high-tech polymers. This shifts the very goal of engineering from creating a perfectly static object to designing a dynamic system that can maintain itself. This philosophy extends to the entire life cycle of a structure. The ancient tradition of continuous, communal upkeep is now reflected in the modern concept of design for disassembly and repair. Instead of building monolithic structures that are destined for the landfill, forward-thinking architects are creating buildings and bridges with components that can be easily inspected, replaced, or upgraded. A worn bearing or a cracked panel can be swapped out without demolishing the entire edifice, mirroring the way medieval communities would replace a single stone on their local bridge. We even see this in bridges that use shape-making principles directly inspired by ancient Roman and Chinese arches, creating graceful, efficient forms that use less material to achieve greater strength. So, how can these ancient ideas inform our future? They offer a blueprint for a shift in mindset, from building cheaply and quickly to building wisely and for the long term. It is a fusion of timeless intuition with modern computation, proving that the path to a sustainable future may very well be paved with ancient stones. That image of 1,000,000 slaves straining to lift colossal stones is a powerful story, but it is often a misleading one. While forced labor was a grim reality of the ancient world, the intricate work of bridge building relied overwhelmingly on the hands of highly skilled, paid artisans. These were not anonymous laborers. They were master masons, carpenters, and engineers who possessed knowledge passed down through generations, their expertise as valuable as any modern degree. They were the ones who understood how to shape a keystone, how to mix the perfect hydraulic mortar, and how to read the subtle settling of an arch. To reduce their monumental achievements to mere brute force is to miss the point entirely. Their work was a craft, an intellectual pursuit as much as a physical one. Another persistent myth is that these bridges are untouched relics, frozen in time exactly as their builders left them. The truth is far more interesting. The Pont du Gard had its water channel narrowed in the 9th century. London Bridge was a perpetual construction site, its houses and shops constantly being rebuilt and replaced. This was not a failure of the original design, it was its ultimate success. The fact that these structures could be repaired, adapted, and reused for centuries is a powerful testament to their inherent flexibility and robust design. They were not fragile monuments, they were resilient frameworks that invited future generations to participate in their story. Perhaps the most enduring misconception is that ancient builders simply overbuilt everything, throwing endless stone at a problem until it finally stood. The reality is a story of remarkable refinement. Yes, the safety factors were generous, but the proportions were often optimized through generations of hard-won experience. Look at the evolution of Roman bridge piers. They grew thicker not out of ignorance, but because earlier, slimmer piers had been scoured away by floods. This was not overbuilding. This was precision engineering, calibrated by the brutal feedback of the real world. Their mass was a deliberate, calculated response to the forces they knew they would face. Why do these myths persist? They create a comforting distance, allowing us to see these builders as primitive rather than peerless. But when we clear away the romanticized fiction, we are left with something far more valuable. We see the true contours of their genius, not in mythical super strength or magical stones, but in the intelligent, adaptable, and deeply human system of knowledge that turned rock and mortar into timeless sentinels. The enduring legacy of these ancient bridges is a powerful testament to human ingenuity. It was never a single secret that granted them millennial life, but a perfect, interlocking system of intuitive design, masterful craftsmanship, and a profound respect for the materials and forces of the natural world. From the geometric perfection of the Roman arch to the renewable wisdom of the Inca rope bridge, we uncover a universal truth. True longevity is not achieved by conquering nature, but by cooperating with it. These structures stand as a quiet rebuke to our modern obsession with speed and disposability, teaching us the immense value of patience, the necessity of maintenance, and the wisdom of designing for resilience over short-term efficiency. As we now confront the global challenges of climate change and resource scarcity, the lessons etched in stone and woven into grass are more vital than ever. They offer a blueprint for a sustainable future, reminding us that the most advanced engineering sometimes looks like a 2,000-year-old curve or a 500-year-old tradition of communal care. Let these ancient sentinels inspire you to look at the world around you with new eyes, to see the hidden intelligence in the old and the enduring. If you found this exploration of timeless engineering fascinating, please subscribe for more journeys into historical mysteries. We would love to hear which ancient bridge amazes you most, so share your thoughts in the comments